Let's continue from the previous video. So we were learning about the mixing and propulsion of food in the stomach, basic electrical rhythm of the stomach wall. As long as food is in the stomach, weak peristaltic constriction waves called mixing waves begin in the mid to upper portions of the stomach wall and move toward the antrum about once every 50 to 20 seconds. These waves are initiated by the gut wall. Basic electrical rhythm consisting of electrical slow waves that occur simultaneously in the stomach wall. As the constrictor waves progress from the body of the stomach into the antrum, they become more intense. Some become extremely intense and provide powerful peristaltic action potentials, driven constrictor rings that force the antrum contents under higher and higher pressure toward the pylorus. And this constrictor rings also plays an important role in the mixing of stomach contents by digging deeply into the food contents in the antrum. During gastric motility, most of the antral contents are squeezed upstream through the peristaltic ring towards the body of the stomach, not through the pylorus. Thus, the moving peristaltic constrictor ring combined with this upstream squeezing action is called retropulsion, is an extremely important mixing mechanism in the stomach. After food in the stomach has become thoroughly mixed with the stomach secretions, the resulting mixture that passes down the gut is called chyme. The appearance of chyme is that a murky, semi-fluid or paste-like structure. Then, hunger contractions. Beside the peristaltic contractions that occur when food is present in the stomach, another type of intense contraction called hunger contractions often occur when the stomach has been empty for several hours or more. These contractions are rhythmic peristaltic contractions in the body of the stomach. Hunger contractions are most intense in young, healthy people who have high degree of GI tonus. They are also greatly increased by the person having lower than normal levels of blood sugar. When hunger contractions occur in the stomach, the person sometimes experiences mild pain in the pit of the stomach called hunger pangs. Pangs usually do not begin until 12 to 24 hours after the last ingestion of food. In people who are in a state of starvation, they reach their greatest intensity in 3-4 days and gradually weaken in succeeding days. Then stomach emptying. Stomach emptying is promoted by intense peristaltic contractions in the stomach antrum. At the same time, emptying is opposed by varying degrees of resistance to passage of chyme at the pylorus. Intense antral peristaltic contractions during stomach emptying is the pyloric pump. Most of the time, the rhythmic stomach contractions are weak and function mainly to cause mixing of food and gastric secretions. However, for about 20% of the time, while food is in the stomach, the contractions become intense, beginning in the mid-stomach and spreading through the caudal stomach. These contractions are strong peristaltic, very tight ring-like constrictions that can cause stomach emptying. The intense peristaltic contractions often create 50 to 70 centimeter H2O pressure, which is about 6 times as powerful as a usual mixing type of peristaltic waves. When pyloric tone is normal, each strong peristaltic wave forces up to several milliliters of chyme into the duodenum. The peristaltic waves, in addition to causing mixing in the stomach, also provide a pumping action called the pyloric pump. The role of the pylorus in the controlling stomach emptying. The distal opening of the stomach is the pylorus and consists of circular muscles. It remains slightly tonically contracted almost all the time. Therefore, the pyloric circular muscle is added, called the pyloric sphincter. Despite normal tonic contraction of the pyloric sphincter, the pylorus usually is open enough for water and other fluids to empty from the stomach into the duodenum with ease. The degree of constriction of the pylorus is increased or decreased under the influence of nerves and hormonal signals from both the stomach and the duodenum. Regulation of stomach emptying. The rate at which the stomach empties is regulated by signals from both the stomach and the duodenum. So factors that influence gastric emptying include gastric or duodenal factors such as gastric factors that promote emptying, like gastric food volume. Increased volume causes stretching of the stomach wall eliciting local meandric reflexes. This attenuates the pyloric pump and inhibits the pyloric sphincter, which promotes increased emptying. Then gastrin has mild to moderate stimulatory effects on motor functions of the body, of the stomach, and importantly enhances the activity of the pyloric pump. Then powerful duodenal factors that inhibit stomach emptying. Enterogastric nerve reflexes strongly inhibits the pyloric pump. Impulsive contractions also increases the tone of the pyloric sphincter. Hormonal feedback from the duodenum. Fats entering the duodenum stimulate inhibitory hormone, primarily CCK, which inhibits the pyloric pump and increases the tone of the pyloric sphincter. Then secretin, acidic chyme stimulates the release of secretin, which in turn is responsible for the inhibition of gastric motility. Then gastric inhibitory peptide GIP has a general but weak effect on decreasing gastrointestinal motility. Then regulation of stomach emptying. The rate at which the stomach empties is regulated by signals from both the stomach and the duodenum. However, the duodenum provides by far the more potent of the signals, controlling the emptying of chyme into the duodenum at a rate no greater than the rate at which the chyme can be digested and absorbed in the small intestine. The feedback inhibitory mechanisms work together to show the rate of emptying. When too much of chyme is already in the small intestine, the chyme is extremely acidic, contains too much unprocessed protein or fat, is hypertonic or is irritating. The factors that regulate gastric emptying is already mentioned earlier. Then powerful duodenal factors that inhibit stomach emptying. Inhibitory effect of enterogastric nerves reflexes from the duodenum. When food enters the duodenum, multiple nerve reflexes are initiated from the duodenal wall. Those reflexes are mediated by three routes directly from the duodenum to the stomach through the enteric nerve system in the gut wall, through enteric nerves and extrinsic nerves that go to the prevertebral sympathetic ganglia and then back through inhibitory sympathetic nerve fibers to the stomach, probably to a slight extent through the vagus nerve all the way to the brainstem. Then they inhibit the normal excitatory signals transmitted to the stomach through the vagi. All these parallel reflexes have two effects on stomach emptying. First, they strongly inhibit the pyloric pump propulsive contractions, and second, they increase the tone of the pyloric sphincter. The type of factors that are continuously monitored in the duodenum and that can initiate enterogastric reflexes are summarized. And then hormonal feedback of the duodenum inhibits gastric emptying. Role of fats and hormone cholecytokinin. Besides the nerve reflexes from the duodenum that inhibit stomach emptying, fats entering the duodenum stimulate inhibitory hormones to be released from the upper intestine. In turn, these hormones are carried by way of the blood to the stomach, where they inhibit the pyloric pump and at the same time increase the strength of the contraction of the pyloric sphincter. The most potent of this enzyme hormone appears to be cholecytokinin, which is released from the mucosa of the jejunum in response to fatty substances in the chyme. Factors that need to be monitored in the duodenum. The type of factors that are continuously monitored in the duodenum and that can initiate enterogastric inhibitory reflexes include the distension of the duodenum, the presence of any irritation of the duodenal mucosa, acidity of the duodenal chyme, osmolarity of the chyme, and the presence of certain breakdown products in the chyme, especially breakdown products of proteins and perhaps to a lesser extent of fats. The most potent of the hormones appears to be cholecytokinin, which is released from the mucosa of the jejunum in response to fatty substances in the chyme. Other possible inhibitors of stomach emptying are the hormones secretin and glucose dependent insulinotropic peptide, also called gastric inhibitory peptide. Secretin is released mainly from the duodenal mucosa in response to gastric acid passed from the stomach through the pylorus. GIP is released from the upper small intestine mainly in response to fats in the chyme, but to a lesser extent in response to carbohydrates as well. GIP has general but weak effect of decreasing GI motility. However, the main effect of physiological concentrations is probably mainly to stimulate secretion of insulin by the pancreas. Movements to the small intestine. The movements of the small intestine, like those elsewhere in the GI tract, can be divided into mixing contractions and propulsive contractions. To a great extent, this secretion is artificial because essentially all movements of the small intestine cause at least some degree of both mixing and propulsion. The usual classification of this process is described in the following sections. Mixing contractions, like segmentation contractions, when a portion of a small intestine become distended with chyme. Stretching of the intestinal wall elicit localized concentric contractions spaced at intervals along the intestine and lasting a fraction of a minute. The constriction causes segmentation of the small intestine. They divide the intestine into spaced segments that have the appearance of a chain of sausages. As one set of segmentation contraction relaxes, a new set often begins, but the contractions this time occur mainly on new points between the previous contractions. Therefore, the segmentation contractions chop the chyme 2 to 3 times per minute, in this way promoting progressive mixing of the food with secretions of the small intestine. So regularly spaced regions, isolated regions, regularly spaced regions, and weak regularly spaced regions. This indicate the segmentation movements of the small intestine. The maximum frequency of the segmentation contractions in the small intestine is determined by the frequency of electrical slow waves in the intestinal wall, which is about 12 minutes. But this maximum frequency occurs only under extreme conditions of stimulation. In the terminal ileum, the maximum frequency is usually 8 to 9 contractions per minute. Then propulsive movements. Next topic is about propulsive movements. Peristalsis is in the small intestine. Chyme is propelled through the small intestine faster in the proximal intestine and slower in the terminal intestine. Peristaltic waves are normally weak and usually die out after traveling only 3 to 5 cm. Movement of the chyme is very slow, so slow that the neck movement along the small intestine normally averages only 1 cm per minute. This rate of travel means that 3 to 5 hours is required for passing of chyme from the pylorus to the ileocecal valve. Next, peristaltic rush. Although peristalsis in the small intestine is normally weak, intense irritation of the intestinal mucosa, as occurs in some severe cases of infectious diarrhea, can cause both powerful and rapid peristalsis called the peristaltic rush. This phenomenon is initiated partly by nerve reflexes that involve the autonomic nerve system and the brainstem, and partly by intrinsic enhancement of the meningic plexus reflexes within the gut wall. The powerful peristaltic contractions travel long distances in the small intestine within minutes, sweeping the contents of the intestine into the colon and thereby retrieving and relieving the small intestine of irritative chyme and excessive distension. Movements caused by the muscularis mucosae and muscle fibers of the villi. The muscularis mucosae can cause shortfalls to appear in the intestinal mucosa. In addition, individual fibers from this muscle extend into the intestinal villi and cause them to contract intermittently. The mucosal folds increase the surface area exposed to the chyme, thereby increasing absorption. Also, contractions of the villi, shortening, elongating, and shortening again, milk the villi so that lymph flows freely from the central lacteals of the villi into the lymphatic system. This mucosal and villus contractions are initiated mainly by local nerve reflexes and the submucosal nerve plexus that occur in response to chyme in the small intestine. The ileocecal valve prevents backflow from the colon to the small intestine. The principal function of the ileocecal valve is to prevent backflow of fecal contents from the colon into small intestine. The ileocecal valve protrudes into the lumen of the cecum and therefore is forcibly closed when excess pressure builds up in the cecum and tries to push cecal contents backward against the valve lips. The valve usually can resist reverse pressure of at least 50 to 60 cm H2O. So when we just try to look at the emptying of the ileocecal valve, we can see that colon region is there, ileocecal sphincter, valve, ileum. Pressure and chemical irritation relax sphincter and excite peristalsis. Fluidity of contents promote emptying, and pressure or chemical irritation in cecum inhibits peristalsis of ileum and excites sphincter. Then summary of intestinal movements along the GI tract: small intestine, large intestine, and small intestine. Type of motility include mixing of segmental contractions. Then these are located and localized concentric concentrations spaced at intervals along the intestine and lasting a fraction of a minute. Then peristalsis, propulsive movements of the small intestine that propel the chyme towards the anus. Then movements caused by muscularis mucosae, villi movements, mixing movements, and propulsive movements like mass movements. The wall of the ileum for several centimeters immediately upstream from the ileocecal valve has a thickened circular muscle called the ileocecal sphincter that normally remains midly constricted and slows emptying of ileal contents into the cecum. Normally only 150 to 2000 ml of the chyme empties into the cecum each year. Feedback control of the ileocecal sphincter. The degree of contraction of the ileocecal sphincter and the intensity of peristalsis in the terminal ileum are controlled significantly by reflexes of the cecum. When the cecum is distended, contraction of this ileocecal sphincter becomes intensified and ileal peristalsis is inhibited, both of which greatly delay emptying of additional chyme into the cecum from the ileum. Also, any irritant in the cecum delays emptying. For example, an inflammation appendix can cause such intense spasm of the ileocecal sphincter and partial paralysis of the ileum that this effects together block emptying of the ileum into the cecum. The reflexes from the cecum to the ileocecal sphincter and ileum are mediated both by way of the myenteric plexus and by the extrinsic autonomic nerves, especially by way of a preverbal sympathetic ganglia. And then movements of the colon. The principal functions of the colon are absorption of water and electrolytes from the chyme to form solid feces, proximal half of the colon, and storage of fecal matter until it can be expelled, distal end of the colon. Although the movements of the colon are normally sluggish, they still have characteristically very similar to those of small intestine and can be divided once again into mixing movements and propulsive movements. There are many types like mixing movements. Hastrations. In the same manner that segmentation movements occur in the small intestine, large circular constrictions occur in the large intestine. At each of these constrictions, about 2.5 centimeter of circular muscle contracts, sometimes constricting the lumen of the colon almost to occlusion. At the same time, the longitudinal muscle of the colon, which is aggregated into 3 longitudinal stripes called the tenae scoli, contracts. This combined contraction of the circular and longitudinal stripes of muscle cause the unstimulated portion of the large intestine to bulge outward to a bag-like sac called hastorations. Each hastoration usually reaches peak intensity in about 30 seconds and then disappears during the next 60 seconds. Therefore, the fecal material in the large intestine is slowly dug into and rolled over in such a manner, same manner that one spades the earth. In this way, all the fecal material is gradually exposed to the mucosal surface of the large intestine, and fluid and dissolved substances are progressively absorbed until only 80 to 200 ml of feces are expelled each day. Then propulsive movements, mass movements. Much of the propulsion of the cecum and ascending colon results from the slow but persistent haustorial contractions, requiring as many as 8 to 15 hours to move the chyme from the ileocecal valve through the colon, while the chyme becomes fecal in quality. Then ileocecal valve, fluid, semi-fluid structure, and mush, semi-mush, and semi-solid, solid. So poor motility of this absorption and storage functions of the large intestine. Poor motility causes greater absorption, and hard feces in transverse colon causes constipation. Excess motility causes less absorption and diarrhea or loose feces. Then mass movements. Much of the propulsion of the cecum and ascending colon results from the slow but persistent haustral contractions, requiring as many as 8 to 15 hours to move the chyme from the ileocecal valve through the colon, while the chyme becomes fecal in quality. From the cecum to the sigmoid, mass movements can, for many minutes at a time, take over the propulsive role. A mass movement is a modified type of peristaltic characterized by the following sequence of events. A constrictive ring occurs in response to a distended or irritated point in the colon, usually in the transverse colon. Then rapidly the 20 or more centimeters of colon distal to the constrictive ring lost their hastrations and instead contract as a unit, propelling the fecal material in the segment en masse further down the colon. The contraction develops progressively more force for about 30 seconds and relaxation occurs during the next 2 to 3 minutes. Another mass movement then occurs, this time perhaps further along the colon. A series of mass movements usually persist for 10 to 13 minutes. Then they cease but return perhaps in a half day later. When they have forced a mass of feces into the rectum, the desire for defecation is felt. Initiation of mass movements by gastrocolic and duodenocolic reflexes. The appearance of mass movements after meals is facilitated by gastrocolic and duodenocolic reflexes. These reflexes results from distension of the stomach and duodenum. They occur either not at all or hardly at all when the extrinsic autonomic nerves to the colon have been removed, and therefore the reflexes almost certainly are transmitted by way of the autonomic nerve system. Irritation of the colon can also initiate intense mass movements. For instance, a person who has an ulcered condition in the colon mucosa frequently has mass movements that persist almost all the time.